YouTube. Welcome back. Today I have Mike Fikes with me. Ben couldn't be with us. How you doing, Mike?
Good. How you doing, man? It's been a while.
Good, good. Well, we just spent half an hour talking electronics, which is always fun to do. And Mike and I met, what, about a year and a half ago, year ago?
It must have been. It might have been 2 years ago. I remember it was
2 years ago already?
It was winter time. I don't know. Time is flying.
Yeah. It was about 6 PC boards ago.
Yes, that's the measure of time.
Yes.
Rev A, Rev B, or whatever you call it, Rev 1, Rev 2.
What do we call that circuit board? I've already forgotten it. Not cricket.
You called the very first one the pawn, I think.
Pawn, because it was your opening move, in chess.
And then you called one of them a chirp.
Yeah,
and
that's it, chirp.
Was that because we were doing UWB, maybe? Or I can't remember what the...
It was talking in chirps or something like that.
Okay,
yeah.
It was chirping, yeah.
Yeah.
But yeah.
So, so when you and I met, you did not have a table full of equipment behind you.
That's true. To me, at the time, this was a burgeoning hobby. And right around the time when I met you was, for me, a transition between it being a fun thing to learn about at home and actually becoming important at work.
Right.
And lucrative in a sense, like I could justify buying stuff. Now all the gear I bought, like yours, is largely older, cheaper stuff. I can,
Right. Yeah.
There's no
I can't afford my equipment if it were new. No, absolutely.
Yeah, it's like I feel like I was thinking about this the other day. If I had this stuff back in the 80s, I would be a millionaire, right? It's like the prices of this stuff is like only labs could afford to buy.
Well, and that's why as a hardware engineer, I had to work for somebody. I would have needed, an oscilloscope was a year's pay. I would have needed $40,000 worth of equipment just to do anything at all, just in meters and an oscilloscope and whatnot.
So you would actually have to go into work. You would have to be in the lab to do. I mean, you could go home and think. Although you didn't go home back then in those days.
No. Well, the one thing I brought to the table was I had an enormous data book collection. And that was real important because there was no internet. And so not only did you have to have the books that contained the different solutions, you had to have read them. You had to have gone through them and put little index tags in your head to go, I've seen that before. Oh, don't do that. That's a bad thing. Oh, there's a part that does this. All those things came from owning this huge collection of data books that I still have. And it's in some ways it's embarrassing. There's like, oh, here's a data book for an 8-bit chip processor made by National back in '82. Well, who cares, right? So.
What I find odd is when I was younger, I used to think like, man, what was it like back in the day, before all this technology that we have when I was like a teenager. And like, I wonder what life was like back then. And now I've reached an age where I'm like, things have changed enough now where I'm having a hard time remembering what things were like when I was young. It's like, how did you, like little things that you used to just do, like going to a movie, right? You remember like you would look up what was playing in the newspaper and say like, oh, here's the movie times for this show and that show, and you'd like see. I guess you weren't going to movies back then, but
I gave my stereo to my son, right? Going, this will be the only way he can listen to music like I did. I saved for a stereo. It was $500, a Yamaha. Still have it. I go and give that in speakers, right? Mm-hmm. Speaker stands if you live anywhere near other humans.
Yes.
And and I gave it to him, and he wasn't overjoyed. In fact, he ignored it. I took it back and put it back in
MP3s or whatever.
No, he plays music wherever he's at. Yeah, he plays on his computer, his iPad, his phone, and he's using earbuds and stuff. And so it's like, wow, that changed. What was an important part of my growing up culture was rock and roll.
Yes.
Music. He's got it everywhere he goes. And streaming.
I'm now getting into some of the earlier Pink Floyd albums, and I'll just sit there and listen to them. Right? It's like you focus on the music.
Long version of Echoes off the Metal album.
Yeah.
Yeah. Yeah,
That's a
I'm not
long
going to
song,
tell you
too.
to do hallucinogenics and then listen to it. But back in the 70s, that's what you did.
Yeah.
So enough about hallucinogenics.
Yeah.
Let's talk about test equipment. You've got some new pieces in addition to everything behind you, but you recently purchased an SMU. Tell us about that. What is an SMU and what's it stand for?
It's a source measure unit, and I will switch screens so you can see it. I have one
Okay.
on my bench right behind me, but I got a little camera there. Let's see.
Now there's going to be a glitch while we do this. Skype is not nice anymore.
Yeah.
See,
it should be
there's
up
the blue
right
thing
now.
we're talking about.
And cross
And
your fingers.
last time with Alan, we couldn't even get to do a three-way correctly.
Yeah. So do you see
I do.
some stuff on my bench now instead of me? So that's an SMU
Yes.
in the lower right there. And it's Keithley. I think that one is the 2400, which is probably the most popular or iconic SMU. It's a piece of gear from, I don't know, that's probably from the 80s or whatever, 90s.
Well, I love Keithley, and I have a Keithley meter just because it was when we did load cell stuff back in the old days. To get a 5.5 digit meter, we needed places like Keithley. They just wasn't a lot out there.
Yeah. So yeah, and I remember you said you explained to me that one brand was good for measuring and one brand was good for creating signals, I think.
Oh yeah, so I
for
use
60?
on my bench.
Yeah.
I use HP for signal generation. I use Tektronix for scopes. Yeah, that's just me. And I see behind you, you have an HP. Actually, it looks like one of the ones I probably have.
Oh yeah. I'm gonna switch back to me real quick because I'm gonna show
Right.
I'm gonna show a curve tracer, which might help explain parts of the idea of an SMU. So here's a curve tracer here. I'll turn up the brightness, and it's got a diode on it, like the typical thing. And what you're
Right.
seeing there is the IV curve. Horizontally would be the voltage.
Voltage,
So,
right?
and it's basically just it's hooked up to. There's a transformer hooked up to mains in this old unit, and it's just kind of going back and forth in voltage.
Right,
And,
right.
and it's sending that through. There's a diode on there, so what you're seeing is the current that's flowing through that diode. Typical IV curve.
So the voltage keeps going up as it goes from left to right
Yes.
until it hits a point where the diode turns on,
Yeah.
and then the current goes up in one step.
Yeah,
is what
and
we're
you can't
seeing
see
there.
the gradicules
So
because
it's
it's so
point.
far away.
Right.
So I'm turning the voltage knob right now, kind of adjusting that. But
Now,
yeah,
can you read out on that what the
Yes.
forward voltage drop of that diode is? Can you read out on that?
Yeah, so what I can see is it goes up, and then the first gradicule line going up is one milliamp going up, because I can control that as well. And I can see where
Right.
this thing goes up, and it crosses the 1 milliamp line is 0.6. Yeah. like you
0.6.
would- Yeah.
Now, have you tried it with a blue LED?
Yes. And you have to go
And
much
did you
farther out.
get
Yeah.
like 2.2 volts, something like that?
Yeah.
Very good. Yeah.
So the
Yeah,
relevance of this
people
to-
wonder why you can't power a blue LED from a batteries, these small batteries.
Oh, yeah.
And it's quite simply the forward voltage drop is greater than your power supply sometimes. Or if you have a 3-volt supply, 1.8, forget it. 3-volt supply, you don't have a lot of room in there to power a blue LED without, doubling the voltage or doing other tricks. You got some room, don't get me wrong.
Okay. Yeah. And there's no real the forward voltage drop is kind of a little bit ill-defined, because you have to talk about how much current do you want to measure it at. And I have a Keithley and whatever that can measure the forward voltage drop, but you can go in and you can go into the settings and say, oh, measure it at 1 milliamp or a tenth of a milliamp or whatever, and it'll give you the different
Right.
answers. Yeah.
Yeah. Now, when I play with 1N 4001s, 1N 4004s, I tend to use a volt just mentally. My drop-in voltage is a volt, because once you put it under heavy current, there's an additional voltage drop from the IR, the resistance of that junction. And so it may start at 0.6 volts, as you're saying, at a real low current. But if you at 1 amp, it's like a volt.
So now that you mentioned that, I have two different diodes in here. One is a germanium diode, and one is a silicon. So if I crank this out, so you can probably see the crossover point farther out. Let me turn up the intensity maybe, so it's nice and bright. I'll probably burn out the screen, but anyway, you can see it. And I'll flip to the other diode.
Yeah.
See how it moved? That's the germanium diode. It's closer to 0.
Right.
And if I go the other way,
Now-
it's farther out. Yeah.
Now, back in the 80s, if I wanted 0.3 volt drop, I had to use germanium. There was no such thing as a hot carrier Schottky diode that at least I knew about or could afford. Now, that's not quite true. My, where is it? My grid dip meter, which has moved again. I don't know why my grid dip meter keeps moving. That was the first hot carrier Schottky diode I ever saw, and it was probably expensive. And it was big. It was in one of the top hat cases, TO51 or some oddball thing. But no, we had to use germanium diodes, and we didn't mind. Nowadays, you barely ever see a germanium diode. But it had 0.3 volt drop.
So what this curve tracer is doing is it's sourcing. It's creating
current.
A voltage. It's sourcing current and voltage. So if you look at it, you could think of there's like mathematical quadrants. If you like split this into 4 ways, and this diode is going up into the upper right quadrant.
Right.
And if you could zoom in, you could see it's going into the lower left quadrant as well. You know, if you put a zener in there, if you imagine like you go far to the left and then it goes down.
Okay. Now, let me ask you a question. 5 volt zener.
Yes.
That's not a question, it's a statement. But a 5 volt zener is not a zener diode.
Yeah. So what is that? Avalanche?
It's an avalanche diode.
Okay.
It's a different mechanism. It does the same thing, but it's a different mechanism. So zener stuff poops out around 4 volts. After that, it becomes avalanche. And avalanche, if you can picture that, is a lot like it sounds. Is where the carriers basically avalanche across the barrier between the P and the N junction. So there's some physics at work is the way I picture it. And I could stand corrected on that.
No, I remember reading, I can't explain it now, but I remember reading it has to do with quantum mechanics too.
Yeah. And when we say hot carrier, my poor memory these days, is that is actually a velocity of an electron type of thing. And it that's how it works, is it depends on the geometry and these electrons, you know, the speed of them and whatnot, it becomes the mechanism.
Okay.
So
this stuff is fascinating, and so I find having a curve tracer is an unnecessary thing in life, but it's cool to have, and it's great.
Well, you got to fix it too. You got to fix it.
Yeah. So
and so that you learned something from that too.
When I bought it, it had no transformer in it, so I put a new transformer. I bought a doorbell transformer and put that in there, which is like a. You know, the one when you push your doorbell, when you push
it's hard to find transformers. We used to go to Radio Shack, and I had a Stancor catalog that sat on my desk. And, you know, to get a 6.3 volt transformer, you trip over them out in the street. But these days, to get something, you're right, you probably end up at Home Depot, and, you know, since there's no Radio Shack these days.
And when I did that, when I put that transformer in there, there's really funky grounds in there, and I think I hooked up the ground the wrong way. Anyway, there's a few TTL chips in there, and I got it so that it was like, instead of supplying 5 volts, it was supplying -7 volts somehow to the TTL chips, and every last TTL chip in there fried.
They hate that.
All 7 or 8 couldn't cope with that.
Right. So well, now you know why I put reverse diode things on almost every project I work on, is because the way to blow up every single chip in the project is to reverse the power leads. It just blows them up.
Yeah. So I did a lot of eBay purchases to get old diodes. I'm sorry, old TTL chips to put back in there. But it's,
what kind did you need?
It's just 7400 logic, you know. And I don't know if you really need that. You could probably put some LS chips in there. I put some of those in certain places, and it works.
Right.
But to be honest, there are some things in there that are like this weird, unholy mixture of TTL and analog.
TTL and analog. I was going to ask about that. Yeah.
And I was looking at some of that stuff, and I'm like, this doesn't look right. You're not allowed to do this. You know, there's no TTL signals here that you're. Yeah. And I think your view was like they just knew that there were transistors inside the chips, and they right.
I was going to say, you don't black box the chip, and that's, if anybody's familiar with my background, that was how I survived at places like Commodore, where we made chips and computers. Is you'd follow the circuit when it got to the chip. You kept mentally following the circuit. You didn't stop at the chip border. You know, at least you went in as far as the driver and the pre-driver in your thought process.
Okay. And I imagine
Huh.
a lot of this stuff, I think this thing was like from the early 70s. So TTL had probably
Yeah.
just
Yeah.
come out, or so there's back then those engineers knew the low level inner details of those chips. They didn't think about it like the way I do, which is like this interface you need to abide by, and
Right.
certain
Right.
levels and
Right.
whatnot.
And I do that a lot with the CMOS chips, the CD4000 series.
Uh-huh.
I've hooked the VCC and ground together on the chip on a 4066. There was a way to make it look like 4 discrete MOSFETs by hooking VCC to ground out of a quad bilateral switch, I think. And then you had access, and it was something I learned out of Popular Electronics. It's funny, before the internet, we had magazines, so
Yeah.
you would religiously. And then when I was done with the Popular Electronics, I would cut the little I would cut the schematics out, and I stored them in a file cabinet I carried around with me. So I was like a 1970s version of a geek at one point, I think, with long hair.
Yeah, and back then there was no internet, so you couldn't find any other geeks to talk to about it, right? You were kind of all by your lonesome reading these books and learning it as much as you can. And then
Right,
you'd go
right.
to work maybe and you talk to other people there and like talk to Haney and who not.
Right.
Yeah.
And of course, the only place you did technology in the 70s was like TVs. So I became a
Okay.
TV repairman. So I did get to hang out with other people that knew electronics.
TV folk, yeah.
Yeah, but we weren't designing; we were fixing. So my background
yeah.
was fixing, which makes you a good designer. I honestly believe.
That's what I'm. So a lot of this old gear, part of my justification for digging into it is that it helps you learn how things work when they're
Yeah.
broken, and you're like, you have to pull out the schematics, and you're like, what is this part of the schematic really doing? Well, why did they design it that way? And it's the best way to learn, right? You're like, and you're trying to find like, what's the piece that's broken, and what are the techniques you use? Yeah, that's the best way to learn, I think, is when something's broken.
Right. So tell us about the SMU then.
Okay.
So,
Yeah.
we got the idea of quadrants a little bit
Let me
here.
flip back to the
Yeah.
SMU. Yeah. So an SMU is special in that it can go in all the quadrants, basically. Let me see if I can flip back.
And what's that mean?
So effectively, let's see. Oh, is it showing now? Did it flip? Oh, it's blue now.
It's
okay,
coming.
now I'm going to do
Yeah.
a little thing. Let me press the button. Wait a few seconds. The blue will flip back. Okay. So the way I think about it is the upper right quadrant and the lower left quadrant are basically all about sourcing things, and the other 2 quadrants are about syncing things.
Okay.
So on the bench, I actually have, if I scroll up, as a DC load. That's a load up there, which is basically the opposite of a power supply.
It's a programmable resistor.
Basically, yeah. A fancy programmable resistor. Yeah.
And it's a DC resistance. This is not meant to be an AC impedance at different frequencies. It's supposed to have a somewhat flat response across frequencies, I assume.
Yeah, so you can, at low rates, you can tell it to like have transients. You can say, switch this load on and switch it off. That's not really AC, but it's, that's about the extent of it. Yeah.
Right. There's no capacitors or inductors in there. It's all resistors,
right.
is what I'm really saying.
Yeah.
Okay.
Yeah. If you say like, what is the difference between a DC load and like an AC load, which would be like a 50 ohm terminator, I guess, or something like that, or I don't even know if you can get fancy AC loads that do weird things. But yeah, this is a DC load.
Okay.
So an SMU, if you want to say, like, you don't need an SMU. It's a nice to have kind of thing. An SMU is really like a mixture of a power supply and a DC load and perhaps a multimeter, all combined into one single unit. So if I put the camera back down.
Right.
Let's see. Okay. So it is.
How much did that cost, if you don't mind my asking?
No, I don't mind. So this was $2,000.
Wow. Okay.
And I think that's probably, this is probably the bottom end of the eBay scraping the barrel kind of thing. Like most of them are probably up around 3 or 4. So I got the cheapest one and it worked. They're expensive units, yeah. It's probably one of the most expensive pieces of gear I have. Now that I think about it, like when I think about like my scope or all the other things I have,
right,
they're all cheaper than that.
And so it acts as a power supply and a load, you were saying.
Yeah. So you can, what you basically do is on the right, you basically can say, I want a source voltage or current. And when you do that, you can put in negatives. It doesn't care. As a matter of fact, it's running a GPIP program right now. That's while it's flashing. So that's why I don't want to mess with it, because it's actually doing stuff. And every now and then, if you look closely in the display there below those big numbers, it says I source. And every now and then it'll flip to -1 milliamp. That means it's syncing a milliamp, and it's hooked up to a battery here, a little coin cell battery. So this is stuff that I'm trying to learn for work, is trying to get my mind wrapped around batteries and what happens when you draw a lot of current from them. Because Bill, you and I had worked on UWB, and I didn't know this, but those UWB chips, man, they draw like
they hog. Yeah, but not all the time. It's a chirpy type function, right?
Yes. Yeah. And so I learned from you a little bit. This was here to remind me when I was doing. So this is Bill laughs at me.
I'm laughing because I have stories. Yeah.
Yeah. So when, there was a project Bill and I were working on, and it's an automotive-based project, and it was meant to go off of 12 volts, but it could go off of lower than 12 because we had a regulator in the board, right? And I'm like, okay, I'll do it with 9 volts. I'll put this little, I'll put a Duracell 9-volt battery on the thing, and Bill's like, nope, no, you can't do that. And
probably can't do that. Yeah.
Yeah, I did. It worked, but like I don't know what I was doing to the poor battery at the time. And this was something we wanted
or the frequency. Yeah, you probably fell out of FCC compliance would be my gut reaction to that. The frequency regulation probably went to crap, I would assume.
And what was important is we were shipping this stuff to a customer as a demonstration unit, and they were going to place these things at certain places in the car, and we just wanted it to work, and we wanted it to work for a long time and not like fail. So this was the thing that I think you had suggested, Bill, was to get one of these.
I was going to say that's a pretty good battery for moderately small things, actually. Yeah, the AA cells like that.
So what I found was that I have recently learned a good bit about ESR in batteries and the bad things that happen when you
effective series resistance. Right.
Yeah, and I thought 160 milliamps I thought was not much, but with these coin cell batteries, it's a lot for some of them. They will drop. They have like, okay, so ESR is equivalent series resistance or whatever. It's basically
yeah. What I say? Yeah, I always misspeak during these things.
It could probably be multiple. Whatever we speak English.
Yeah, I said effective, but equivalent. Yeah.
So it's the way you would think about it is whenever you think about these impedance things, you think about the source impedance of your power supply, or like the output impedance of it, or if you're thinking about like other things that you might be putting, like if you think about the opposite, the input impedance of your multimeter, and you want them to be for DC stuff or for voltage, you want low output impedance on your power supply. You basically don't want any ESR. You don't, because it's effectively like as if you were to take your power supply and hook up a resistor to its output.
Right.
You don't want
which makes a voltage divider with your load, which means that the voltage across your load will always be something slightly different than what came out of the power supply to begin with.
So power supplies have very, very low ESR, and I guess another word for that is that they make a stiff output. The voltage does not droop much when you put a load on it.
It shows good load regulation.
Yes.
Which means that the output voltage shouldn't change based on the amount of load it's under.
Yes. And a battery has no regulator, right? It's just there. Maybe it does.
Right.
But it's the opposite. Well, it's more soft than a power supply, and it's got a decent ESR in it. Some of these batteries have like say like 20 ohms, 30 ohms of ESR.
Right.
Now I think with these, like this thing over here, probably has like milliohms of ESR, I would guess. But these coin cells, they have a pretty high ESR, like 20, 30. Right. So what the SMU is doing is it's measuring that right now.
All right. So what's it telling us? What do you? So you've got a
Okay.
coin cell hooked up to it.
So
Is it telling us what the ESR? I see a voltage there, but
yeah.
how do you tell
Okay.
the,
So what I'm
the
having it do,
ESR?
what I'm having
Which
it
is
do,
equivalent series resistance, by the way. Yeah.
okay. So what I'm having it do is it's syncing 1 milliamp, and the cool thing is it's got these terminals on the right are they're the output terminals, and the other two are the sense terminals. So just
Right.
like 4-wire, typical 4-wire stuff. It's using that.
Kelvin. Yeah.
Kelvin stuff, yeah. And so it's basically it's drawing current and then stopping and not drawing current. And as it's doing that, oh man, I don't know if I have this. I don't know if I could switch it to show that. But the well, yeah, you can see it in the big number right there. The voltage is changing. The voltage is changing, and if you look carefully, every time it draws current, it might be out of sync by 1 because I'm driving it with a GPIB program, and I don't know if the display is updating as it's doing this. But basically, as it's drawing current, the voltage drops. And then when you let go and put it back to 0, the voltage rises back up again. And if you take the delta of the two, the change in voltage over the change in current, and divide them,
It's
you'll
about
get a
0.1 volt. Yeah. Right.
So this
So
is,
does it read out resistance directly, or do you have to do it with math?
I do it with math. Yeah.
Okay.
So the SMU can measure resistance. That's a good idea. Like there's a little ohms button on there to measure ohms. But
Yeah, you would think that it could calculate that for you.
I think it might be able to. And the SMU, when you say measure ohms, is I think more like an instantaneous ohms measurement. What I'm doing is I'm taking 2 different readings at 2 different voltage levels or 2 different current levels, and then I'm doing the math to figure out what the ESR would be. And the main point here of doing this is that you can take a battery and you can drain it. You can basically produce an IV curve for it that takes that takes a fortnight to do it, whatever, like days, weeks to drain the dang thing, because you don't want to put it under too much current draw. But you can basically make an IV curve for it, and it's the typical things you might see with batteries, where you see like it goes horizontal for quite a long time as the battery is in its normal happy life, and then near the end it drops off. Right, the voltage just tanks at the very end when the battery's about to die.
Right.
So what this is doing is it's creating a model of the battery. It's discharging the battery, so you can create a model of it that is not only just that IV curve, but it also includes the ESR at all points along the battery, because that's important for if you want to simulate the battery. And there's an instrument above it, which is a battery simulator. And the idea there is that if you are well, let me back up. There was one project I was working on recently where I didn't have the right batteries yet. I ordered them from DigiKey, and they hadn't arrived yet. So I was using my power supply to power this project, this board, and the power supply was too stiff. Like it was happy with doing whatever it needed to do. And I didn't know until right before I was going to ship this to the customer that when I went to plug in an actual battery, the ESR came into play big time. And it basically, the voltage was drooping enough to cause the microcontroller on that board to just like turn off and reboot.
Gray out. Yeah.
Yeah,
brown out.
So I've been on this mission recently to learn more about batteries. Just so I can get my head straight.
Now you're controlling this. You keep saying GPIB,
yes.
Which the old GPIB bus, which is a control bus, IEEE 488, something like that, based bus on the back. So you're actually controlling this right now from what?
Yeah. So there is. Let's see. Move the camera. There is a. I'm sorry if I'm making everyone dizzy. There's a Raspberry Pi sitting on the top.
Okay.
Now you could do this from your computer as well, but basically it's a Python program that's running and talking to. It's doing the math that we talked about. It's sending the commands to the device.
So is it plotting something? Are you plotting a graph or
You
a square
could.
wave, or what are you plotting?
I'm just making it dump it to a CSV file.
Okay.
I can't easily show that, but it's basically as it's going along, it's actually giving status. It's telling, like, these voltage things that you're seeing. It's printing out the voltage that it's at and the ESR, and it'll take all that and put it into a CSV file, which would then be the model of a model for this particular battery.
So you could make an entire curve of current versus voltage.
Yes, and as well ESR.
Well, and from that derive ESR, right?
Yes. Yeah. Well, you kind of need to you need to measure the ESR as you're going along, because it like if you just had voltage versus current, maybe that's an interesting point. Could you figure out ESR from those alone? I think I've convinced myself.
Well, it's the change. It's the delta V. You know, the change in voltage must be due to a resistance somewhere.
Mm-hmm.
So yeah, but I would think you could plot. Knowing you give you a week, you'll have this thing plotting, whether you're using Excel to digest the CSV file or not. Yep. You'll have it plotting the characteristic of a battery. I assume.
And the idea is, instead of, like, what happened to me was I was using a regular power supply, and I didn't have the actual batteries until I got the battery, and then I found, like, oh, there's a big difference between the two. A power supply has no ESR really.
A good power supply.
A good power supply, yeah. So I've been getting into, like, what does it mean to like deal with this problem in a better way? And there's a whole class of other instruments called battery simulators, where you can create these models. And the one that I have doesn't really consume an entire model. But what you can have it do is you can basically have it simulate the ESR.
Okay.
Or you can actually put the ESR into it. There is this one's a really old one. It has a little VFD display here, and you can type in the voltage that you want. And so it's like a PSU plus the ability to put in the ESR that you want, and it has like what is it? FETs or something inside there. I don't know how they're doing it. Somehow they make it have resistance internally inside the machine.
Right.
And you could probably just hook a resistor on the outside yourself, I would imagine, to do the same thing.
Right.
And but the idea is, if you want to, like, simulate how your product behaves under all circumstances, you want to, that you can get even fancier units that will, like, take into account the entire curve over time, and you can have it like this. The instrument itself, like, causes it to drain the battery over time. The fake battery that it's simulating.
Yeah, Kevin asked from the chat channel, doesn't the VI curve change as it discharges? And my answer is, I believe so. Right. As a battery discharges, it does goofy. The chemistry gets involved, is the way I mentally model it. I also model not ESR just as a single resistor, but batteries are composed of cells, and to me, that's each cell has an ESR, and so it probably is. Most of the time you can think of it as a single resistance, but in real life it's probably lots of things in parallel, lots of things going on, I assume.
So I'm going to switch back to myself, because we can talk about some of the pictures in the upper right.
Yeah, let's talk about those.
So essentially, I had described, like, oh, I see that my thing is still on. Let me turn this down so it doesn't burn it out.
Burn it up, yeah.
The battery simulator. So the idea here is what we were talking about is you have this problem where you have a device, a mobile device, that is bursty, and it has pulses. It, like, draws current like 160 milliamps for a short period of time, and then it's done. Right.
Well, even a good source of that, if you want to think about it, is the backlight on on display screens. Those are pulse width modulated. Those are on and then off again.
Okay.
Yeah.
So
and they can be big loads, actually.
Yeah, so at work at Vouch, we're working on putting some of this stuff into, like, key fobs that'll be battery driven. So we're really, we want to make sure we get the battery stuff correct, and using battery simulators helps you like really test the various aspects of it. So part of what the battery simulators do, in addition to being able to actually program it to have an ESR, if you will, from the front panel or through GPIB or whatever, another part of at least this older unit from back then, a claim to fame was that it was ultra fast. It was really good at load regulation. It could deal with these pulses. So I guess you might know better than me, Bill, but well, when this battery simulator came out in the late 90s, and evidently what would happen with GSM phones at the time, which was, I guess, a popular technology back then, the pulses would be short enough where they would happen before the poor PSU knew that it had happened, right? And it couldn't regulate quickly enough.
Right.
And I guess your voltage would just drop with one of those older PSUs, and you'd end up, with behavior that differed from a real battery. So the poor PSUs couldn't keep up. So this particular model that Keithley made, one of its claim to fame was that it could regulate within like 40 microseconds, which
okay.
I want to say, well, I've got some pictures in the upper right. So I was like digging into this, like, what does it mean to regulate that quickly? So I think everyone can see the pictures in the upper right above, Bill.
Right, right.
Those are 3 scope traces. So what I did was I basically said, okay, I want to simulate the UWB thing, but I want to simulate it myself rather than hooking up to a real UWB.
Oh, UWB, by the way, means ultra wideband, and it's an RF technology that is chirpy, hence the word. But it deals in it like many RF transmitters. It deals in bursts these days, as opposed to a continuous wave.
Yeah, and you kind of have to like do your business and be done with those things because of the immense power draw. And it might be true with Bluetooth and whatnot, but I think those are just Bluetooth low energy is just nice to run your battery, I think. I don't know, but whatever. These UWB things will like really kick your battery's butt, right? So I hooked these up to PSUs to see like what would it do. So all I did was I got a 22 ohm resistor and a transistor to just switch it on and off really fast, right? And I put it to my, I hooked up the base of my resistor to my signal generator so I could like spike it for a little bit and turn it on and off. So I think the time scales on these, I can't remember. It's on the order of milliseconds. The time base on these scope traces is on the order of milliseconds, and it's really zoomed in vertically, so it's like 50 millivolts per vertical division. So it's like zoomed in. So what you see is effectively, as the load is turned on, the voltage drops down. That's what you're seeing in all 3 of these traces, like that little short period where it drops down. It's under that load, and then I turn it back off, and it goes back up to 3 volts. So this is simulating, so it's a 22 ohm resistor at 3.3 volts or 3 volts or so. So it's about 100 and something milliamps being switched on and off. And I'm looking at the transients for these different power supplies. And the top one is my very first power supply I ever bought, which is a Corad. Where is it? I think a Corad is sitting around here somewhere. It's one that Dave Jones recommended back in the day, and it's a good power supply. Here it is, right here. This dude here. There's the Corad.
Right.
So if you want a power supply, this ain't a bad one. Get this thing, $100 or so off Amazon, right? Single output. But it's the top chart there. So what you're seeing is, as the load is turned off, you can see some funky behavior in there. And it's not just ringing. Those are ramps as the controller inside here is trying to regulate and seek its way back to 3 volts or whatever.
Right. So it looks like an underdampened control loop.
Yeah.
I don't know if because it's ramped. It's hunting.
It's hunting.
It's what it's trying to do.
Yeah. Yeah. It's like, it's ramping down, and then it's like, oh, I've gone too far, back up again, whatever it's doing. And I don't know if
it's like it's settling time, only with a ramp as opposed to a sinusoidal wave, a sine wave.
Yeah. So
that's pretty significant. What kind of power supply was? Oh, that was the one you just held up.
It's a Corad. It's a pretty hefty thing. It's a linear regulator.
Right.
So but it's got some control circuitry in it, obviously, and yeah.
It's meant to. Yeah. Yeah, it is what it is. It's
I think it's
cheap.
it's good. It's good at like DC.
You could run your 8-track tape player off it probably pretty good.
Yeah.
Just
So,
well, I take that back. We used to the bane of 8-track tape players in the old days was when you had too much series resistance in your battery.
Okay.
You would notice when it goes to change tracks, and
really?
you'd hear it going conk, conk, and because the solenoid would be like 5 times the amount of current than the rest of it. And if your batteries got low in battery powered, yes, we had battery powered 8-track tape players. I had them in the service actually, and so somebody came out with an 8-track tape player that had a manual plunger. And so when it was time to change tracks, you actually manually plunged it. And that way your batteries would last a heck of a lot longer than they would if you were doing and be useful longer than if you were doing the solenoid 8-track tape. Do you remember 8-track tapes? Are you
I was
old
going to
enough?
say, Bill, I thought I was pretty old, but I don't. So I do. I remember my parents had 8-tracks. And they were lying around the house. I'm like, what is this? Because we had cassette tapes back then.
Right.
We'd moved on a little bit. But I remember my dad having an 8-track player and like, yeah. Like what? Each song was on its own track, right?
What the funny things happen to albums when they had to break them up into 4 different tracks, they would cut the song short and do all kinds of funny things.
Oh man. Kids these days.
Yeah. So no, I had a cassette player, and mine was a TIAC. I was very proud of it, and I was like, oh, it handles metal oxide tapes. That was our thing.
Okay.
Was that additional overhead you got? The additional, I guess, permeativity of the media allowed you to have bigger and stronger pulses, which allowed you to turn up the amplitude, which made your noise floor drop. So metal tapes were very valuable for us.
No, I mean, I remember tape recordings were pretty hissy and pretty bad compared to like phonograph records, which were like nice and clear, except for the here and there.
Are you familiar with what Dolby does?
No, but I remember the Dolby technology being on all the gear you could buy back then.
Right.
Put it in the Dolby button.
There's a hiss floor that's just it's always there, right?
Yeah.
No matter what. And so what you do is you make all the amplitudes higher, and then when you reduce it later in the process, you reduce the hiss floor. So basically, it's a way of pre-emphasis, is the way I remember it. So, yeah, that's Dolby. Probably I'll get sued for describing it wrong, but that's basically what it does. Was to try to when it reduced the gain in the final stages, it reduced the recorded hiss. Because magnetic media has a hiss built into it due to the particle size. There's just a certain there's a certain amount of noise built into the way the particles lay on the tape. It's just baked into the media, so to speak. So yeah, my first tape player that I was exposed to when I was young was an actual reel-to-reel. My dad had a woolen sack, reel-to-reel tape, and we would wind that thing up and play music on it, and we just thought this is so cool.
So those were probably higher quality than cassettes in terms of audio quality. This reel-to-reel.
Yeah, it was a bigger media amount, and it ran faster. For that matter, a VCR used as an audio tape player was pretty good. If you think about it, if you increase the speed of the tape, increase the size of the media, you get better resolution, is the way to think about it. So it's not unlike how we record to digital these days. Number of bits expands, and the sampling rate, as those go up, so's the quality. So same thing with magnetic media. So there, more than you ever wanted to know about magnetic media. Oh wait, I didn't realize I'm talking off screen here.
That's fine.
So I've been waving my hands around and whatnot. Hey, so we've got this.
Okay.
So we found the power supply 1 has poor regulation.
Yeah.
Tell us about the other supplies here.
Okay, so the middle chart is a Regal DP 832. I can't remember numbers. Whatever. Yeah, 832, a very popular Regal power supply, and it actually it has a little bit of undershoot and overshoot, but if you look up its specs, it's got it claims to be able to regulate within like 50 microseconds or so, which is about
settling time. Yeah.
It's about the same.
Load regulation over settling time.
Yeah. So it's about the same as like this special battery power, battery simulator that had its claim to fame to being ultra fast, at regulating.
Right.
Modern PSUs like the Regal has ballpark around the same time frame. What's interesting though is like what I find interesting is that undershoot. If you were to zoom in on your scope, that little trough goes all the way down close to 0 volts.
Oh wow.
There's like, and you have to zoom into the nanosecond level. Like when you turn on this load, it's basically a 2N222 hooked up to this 22 ohm resistor, 2N2222 4/2s, and when you turn it on, that dang thing sucks the juice, and there's nothing left. The voltage drops all the way down to close to 0, and then back up again within a nanosecond. And what I found, of course, is if you then take that I'm using these longer Pomona leads that are, like a meter long, basically.
Yeah, that's huge. Yeah.
Yeah. So
that's a dipole antenna. Yeah.
So I took the, this is, and when it's like that, when you're doing this, you can like move them around and you can see that curve change. Like if you twist them together and stuff like that, and reduce the inductance loop area and stuff like that, you can see the lead inductance is coming into play. And if you get rid of that, if you like, take the I was doing this on a breadboard, and you put it like hook it right up to the PSU, then it doesn't go down to 0. It goes down maybe halfway to 0, like So there's still a little bit of inductance somewhere, or even maybe inside the PSU, right? It's like you're asking for a lot of current really quickly.
So inductance would also give us a little bit of inductive kick. It's that, I think that's not just resistance.
End. I think that's the other end when it goes up. Maybe like when
it's
you're
in both directions.
Like it still wants to conduct, right? It's still like you're going conducting.
It's a change of current, right? And it's going to change the voltage to try and maintain a consistent current. So inductive kick works in both directions.
Yes. So that overshoot goes way up above 3 volts. If that matters to your circuit, it's like woo, it's way up there for a while and then back down. So
that matters a lot. Yeah. That matters an awful lot in modern solid state. Yeah. So which is why we end up with like the transorbs. I call them by their brand name.
Okay.
But in the circuitry that you and me have worked on, we've got a voltage clamp in there.
Okay. So I took one of the boards that you had designed, Bill, that has a UWB on it, and I probed it to see like, is it doing this kind of stuff? And it wasn't. It was actually much nicer. Like there were little transients, but nowhere near like this breadboard based thing with flying leads. Yeah.
Which, if we were to show the schematic of the board, though, there was a common mode choke in series with it, and it's resisting changes of current. There's voltage bypass bulk caps resisting changes of voltage. And then we have a voltage clamp on the input because cars, where this was meant to go, are very dirty. They're very yucky power supplies.
Yeah.
Yes.
And I also found like if I took this particular experiment that I had and I put a capacitor on the breadboard, it would further reduce that transient.
Right. And that's probably an instance of bulk capacitance versus what we call decoupling capacitance. You're increasing the bulk capacitance, which is meant to smooth out that power supply initial current flow to the board.
And what this reminded me of is that subject you and Ben had talked about back in the past, which is like the power supply. What's the right word for it? But you make a spectrum of it. It's the PDN. And you can like look at like how do different frequencies come into play for supplying powers. And I think you were talking about FPGAs at the time, and how they have like quick pulses of they need current rapidly,
very
and then
quick.
It goes away.
Yeah, and especially in an FPGA where you have a global clock, and picture all your gates have the ability to go chunk at the same time.
Yeah.
And so synchronous voltage current draws are. Yeah, you have to account for.
So I guess in that thing with the FPGA, you're worried about like perhaps higher frequency jumps and.
So a bulk capacitance makes sure there's enough current to supply it under all loads. And the decoupling capacitor, the definition of decoupling is it decouples the inductance of the trace that got you there. So the decoupling cap is meant to, you might have enough current capability now, because I've got a bulk cap here. You'll see them 100 microfarad or something. But then you have an inductor going to the FPGA. So up near the FPGA, we put another capacitor that decouples that inductor from there. So it restores some of that current delivering. So two slightly, I mean, they're both capacitors, but two slightly different mnemonics for the use of those capacitors.
And that's this thing that got me into this was basically the whole idea of a battery and its ESR and its inability to like provide current quickly. Actually, the ESR, if this, what we're seeing here, is just the ESR of the PSU as it's basically being put under that load. If you were to actually put a real battery on there or have a higher ESR, then that part of the curve where it drops down would be much, much lower. And that's where I was having a problem, was where that long part was down low and the MCU was just turning off.
Speaking of ESR, you and me did the same thing. I called Mike on was it a Sunday? And I was like, Mike, I'm trying to do this. And suddenly I disrupted his day. And you did something similar. Do you remember what we were doing here? This is my VNA.
Okay, yeah, what were we doing back then? Yeah, we were
trying to measure the ESR of a capacitor. We put the capacitor on the leads behind this huge inductor, right?
Yeah.
But we're doing it, just throwing it together. And basically, we were trying to sweep the frequency to get a frequency response curve of a capacitor, you know, before it goes inductive. And the difference between 0 and where the peak ended, we were going, that should be the ESR of the capacitor. So you and me were trying to figure out ESR, see if we could make it a measurable, calculable value from the VNA. And we kind of said we could see it, but I couldn't calculate it, you know, from that result.
Yeah.
Of course, I had these huge inductors and stuff, but...
Yeah, and for me, I was able to put it on the Smith chart and see where it became resonant.
Inductive. Right.
Yeah, where it crossed over from capacitor to reductive. And then my VNA would tell me what the resistance was at that point. But it was so close to the edge of the Smith chart, it was kind of like questionable as to whether or not it was actually measuring it.
Well, and that's the thing I had. By the time I looked at the response, it's not like I could look at it and read it out in ohms, right?
Yeah.
So
the last
so what's
chart
this
there,
bottom? Bottom.
The bottom one is the fancy 90s era battery simulator that claims to have like ultra fast regulation.
Okay.
And if you so you can notice that there's some fuzz on it, right? Some blur.
Now, are these on the same scales?
Yeah, everything is the same scale.
Right. So it does look ultra fast, but then it looks noisy.
Yes. And if you were to pick this instrument up, it's ultra light. There's no toroids in it. If you look inside there, there's no huge capacitors inside there. I think the entire thing is just a big switching regulator of some sort. And I think it has like a high bandwidth mode and a low bandwidth mode, and I think it's basically trying its best to like regulate really quickly and basically willing to put noise into the system to do that. Or I could have a defective unit. It's a dual channel thing, so I could try the other one and see if it does that as well.
You could, a good experiment would be, you know, those things we were talking about, like common mode chokes and the caps and stuff.
Yeah.
If you fed that to one of the chirp, for example, you should be able to scope it and see it get cleaned up, I would bet.
Yeah, I have a bunch of those. You recommended me to get those chokes. I have a whole box of them where I can wrap them around the wires and...
Oh, where is my... I love mine. I have a toroid coil collection around here somewhere. Well, didn't you get one of the big ones too for measuring, for doing conductive measurements?
I did, yeah. Like
huge toroid, yeah.
Yeah. So what I found is like if you take this bottom curve and you put it on like a digital scope and you put it in like its high res mode so that it averages out the noise and makes the noise go away, then what you get is like a almost perfect square wave, right? There's no undershoot, no overshoot. So it's doing whatever it's supposed to do in terms of like quick regulation. But I'm questioning, like, is that noise...
What's all that hashy noise?
It's because that noise is... that the vertical division is 50 millivolts. So that noise is like 100 millivolts peak to peak. It's a lot of noise.
Right.
But it's at about 12 kilohertz or so. So I think there's a switching regulator inside there. I don't know. That's the fun thing about this old equipment. I'm going to go open it up and probe around, or try the other channel to see if it's doing the same thing.
Can you post that model number to Discord? By the way, let's talk about Discord real quick. We have a Discord channel. If you go to Corioliseffect.com, no, right, wrong. Coriolis-effect.com. Hyphen is a dash. There's a Discord invite, and we hang out on Discord, and Mike may post the model number. Yeah. Because I'd like to look that up, because that sounds like a low frequency for a switching regulator, but it's not too far out of the ballpark. Or maybe that's just the frequency they used back then.
I don't know. I'll have to measure it and So I'm still digging into what is that stuff. And it's worth saying also that this is an old battery simulator, right? There's newer ones you can get from Keithley that are fancy touch screen, and they have whiz bang graphics on them. But the cool thing the newer ones will do is, like I said, it will let you put an entire battery model in there, and then you can say, oh, let me pretend like my battery has got this much charge left in it. And you can see is your product failing as the battery is about, because you want your product to I don't know. I guess some of my kids' toys, they would behave really weird when the battery would get weak. Some of those talking toys would start to the microcontrollers in them would start to freak out.
So that's a technique actually for breaking some of the encryption, breaking some of the security on microprocessors. There's supposed to be an unreadable section of the processor, the unique ID and stuff. And they found if they lower the voltage just enough to just crash part of it and then bring it back up, they can now read it and stuff. So you can ink that voltage down there and do funny things to microprocessors. Okay, I'm going to throw one more blast from the past for you, and then we'll call it a day here.
Wrap it up.
So there was a game before video. Well, no, there were video games out, but we played a game called Dark Tower, which I think it was called that.
Okay.
Which had a little 4-bit banger processor in it, and you would turn this tower, and and it had a game board, and you would sit around it, and you would move pieces on a game board. And then you would press a thing, and it would tell you, oh, you attacked, you were wiped out by plague, 20% of your force is gone. But the trick was you'd start out with fresh batteries, and before the battery died, you'd try to finish your game, because what would happen is it'd forget you. It'd forget that you already had the plague or something like that, and it would, suddenly the game's unplayable. And it was like, oh, the batteries are drained, So it's still working. It's still spinning and doing the lights, but it was called Dark Tower. Somebody did. Is that what it was called, Mr. Landfill? Let me get my glasses on.
One of those older games, made by Mattel or whatever.
Mr. Landfill. Yeah. Chris said he had that game. Who was the actor that used to advertise for that? He was known for advertising wine and steak and stuff. The slightly overweight actor. But I just remember the commercials for it, and he's like, I needed food for my troops. And we love that game. We do, we'd put on Pink Floyd metal and play the
before the batteries would die.
Yeah. But we realized even back in the 70s, this when this happened. It's like, 70s, late 70s, early 80s. Wow, this is a battery processor related issue here going on when the batteries get weak. And it affected the memory before it affected some of the other things. So it'd be interesting to see what's in a Dark Tower game now that I've said that. Orson Welles. Orson Welles was who was the spokesperson for that. So, well, hey, Mike, it's been great showing us everybody showing us this. This was excellent. And now I've seen an SMU working. I've never actually seen one, never had one.
You don't need one, but they're cool,
Well, as you pointed out, they're useful for automation. You've taken the GPIB bus, and you can program it to have different loads and do whatnot. And that's real important for automated
all these instruments
testing.
in one, so you don't have to coordinate between 3 or 4 different instruments. It's all in one unit. So that's worth something to you if you're trying to like just program it
Right.
and automate something. Yeah.
Is your GPIB interface, is that handy? Is that it behind you, the yellow box
Yeah,
by
it
any
is.
chance?
So this is if that little yellow
I
thing
got
right there
one
is
somewhere.
yeah.
Yeah.
So these things, this is basically a GPIB to USB bridge
Right.
or converter, if you will. Yeah, and these things they're affordable. I got this one off of eBay for like $80. The lab view ones are really expensive, right? You
Now,
if you bought a brand new nice one, yeah.
I think you can get not made by the National Instruments people, but you can get them for 80, 90 new.
Okay.
Is my memory. Yeah,
Yeah.
'cause I had one of those. I have one of those. I just don't know where it is these days.
Yeah, and I typically don't like to program these things. I just like to use them. But for something like this, if you're going to drain a battery, it's cool. Just program it up and have it
Well,
do.
and
Yeah.
somebody that doesn't mind programming, somebody who doesn't mind a programming language that uses white spaces.
Oh, I can't stand that either.
Python.
Yeah. Yeah.
Terry Ryan sent me a thing. It was like the worst programming language either, and it was about why does this code run and this one doesn't, and the difference were tabs or something.
Oh man, maybe I should get an old Commodore to drive this GPIB stuff and program it in BASIC.
We had an IEEE 488 bus. We absolutely did.
The VIC 20
Because our
had
disk
one.
drives were
Oh man, that's right. I could get an old VIC 20 and just hook it right on in.
go to town. I got one of those too laying around here. So
Oh man.
excellent. Hey, Mike,
Cool,
thank
man.
you
Thank you,
today
Jeff.
for stepping in, and it was interesting
Anytime,
as
yeah.
always.
Yeah.
It's interesting watching that pile of stuff behind you grow as your bank account gets smaller.
It's also it weighs more than me now.
Well,
I'm gonna break this table
strong
one day.
tables. Mine's at the limit. I won't pile more instruments on my table. So, and mine was made for it. So excellent. All right, so we'll be back next week. Ben will probably be with us, and we'll figure out something to talk about then. And thanks everybody for watching. Thank you again, and we'll see you next week.